Let's get ready to rumble! Everyone, it's Miss Sorensen, back with another video, video 9, sample distributions and sample mean. Now, I have to warn you a little bit on this one. This is abstract, and I would say that so far this would be the most difficult video. Math-wise, it's not very difficult, but wrapping your head around what the question is asking and what we're talking about is a challenge. So maybe you want to watch this video twice and make sure you're super focused while watching it. Let's get started. All right. There's 9 people in a family, and they have the following number of shoes. So let's say that Ben's in this family. Ben only has 1 pair of shoes. Let's say that Mom has 2 pairs of shoes. Dad. Okay. And let's see who else. Jean is in the family. Lori is in the family. Tanner. Sam. Kati. And we'll say Cello's 3, 2, 1. All right. Now, this is an entire population. Okay, let's consider this an entire population. Now, in all practicalness, if we wanted to find what the average was for number of shoes in terms of pairs, what the average was for this population, it makes the most sense to go and interview everyone and get their values. But that's not what we're going to do, right? That's not actually practical in a larger population. If we're talking about the population of the world, there's no way we can go out and do that. So this is kind of a theoretical example, but I think it will help you understand what a sample distribution is. So let's say John goes out and he interviews 2 people. He asks Ben and he asks the mom, right? So this was his first sample. John sampled 2 people, and he happened to get interviewed Mom and Ben. And Ben had 1 pair of shoes and Mom had 2 pairs of shoes. So his sample size was 2. Okay, so he has a sample size of 2. And what's the average there? Well, when he sampled 2 people, 1 plus 2 is 3. 3 divided by 2 is 1.5. So he sampled 2 people, specifically Ben and Mom. And when he sampled those 2 people, he got an average of 1.5. Okay, now John also went out and decided to sample 2 more people. So who did he ask? Well, he went out, he asked Ben and Dad. So he found that Ben had 1 pair of shoes and Dad had 3 pairs of shoes. So averaging those, we find that his sample of 2 produced an average of 2 pairs of shoes. Okay, then he went out and he sampled or interviewed both Ben and Jean. So between Ben and Jean, that's going to be an average of 2.5, right? I'm not saying 12, 13, 14. I'm saying 1, 2, 1, 3, 1, 4. All right, now, who did Nate interview? Nate interviewed Mom and Lori. And when he went out, he found that Mom had 2 pairs and Lori had 5 pairs. So that's an average of 3.5. So from Nate's sample size of 2, he got an average of 3.5. But then he also went back and he said, hey, I'm going to sample another 2. And from that, he got an average of 4. Then he went out and sampled another 2 people. There, he got an average of 4.5. Okay? Go ahead and pause this video real quick and continue to average the 2 numbers that are right next to the person's name. All right, pause that video now. All right, I might have made an error in there somewhere, but hopefully that's fairly accurate. Now, all these people went out and did tons of samples, and you would think that like somewhere in there we'd be fairly close to the actual average of the population, or if we looked at this data, we would get mostly answers around the actual average. So let's discuss that in a little bit more detail. The population mean of the numbers 1 through 9. Let's actually find that. And going back to our values here, what would we guess our answer is looking at these? I mean, we've got some low numbers, we've got some high numbers. I'm guessing around 4.5, 5, 5.5 is my guess, but let's actually find it. So remember, someone had one pair of shoes, 2 pairs of shoes, all the way up. Let's go ahead and find the average. So to do that, I'm going to add up all those values, and I get 45. And of course, we have 9 numbers, so we get an average of 5. So this family has an average of 5 pairs of shoes each. And if we look back, does 5 make sense? Yeah, you know, some are low, right? But some are also higher than what the average is. But mainly, we've got a lot of 5s here, all right? We've got numbers that are hovering around 5, like 4.5 and 4.5, okay? So let's say the entire class was in the room, and I said, hey, get your solutions and let's create a histogram. All right, so let's try to figure out where are most of our answers. And, you know, we didn't do this as many times as possible. You know, if we did, we would have had a lot more answers. But in theory, what would this graph look like? All right, someone got an average of 5. Let's see where else we got. 1.5, 2, and 2.5. So we've got a 1.5, 2, and a 2.5. Did anyone else get 1.5, 2, and 2.5? No. We've got a 7.5, another 7.5. Do we have anything higher than that? Okay, another 7.5. Well, I'm not sure, right? So it's going to look something like this, and I'm just giving you a rough estimate. But any guesses as to, you know, what's going to start happening here as we start sampling our 2s? Yeah, you guessed it, right? We're going to basically have more data happening at our population average. Okay, and it's going to just start building up there once we start doing that. So you can see we've kind of got something going on here where notice we've got 5. Not perfect, but we'll discuss what that means in a little bit of detail now. So what is a sample distribution? That's the question. It's very confusing. But let's go back to our original. Everyone went out and got a sample and found the average. John went out and found a sample of 2 people. He got an average. Nate went out. He got a sample of 2 people. He got an average. John went back out, got a sample of 2 people. He got an average. In theory, we can do this not an infinite number of times because the population is finite, but we could do it tons and tons and tons of times until we exhaust all possible samples. All right. So let's go back and say Nate went out and he sampled a bunch of people. Well, he came back with an average. All right. Let's say for a different example, he got an average of, say, 35. I don't know, maybe this is number of chickens you've consumed in the month of January. And then Che goes out and he does a sample of how many chickens people are eating, and they get an average. He gets an average of maybe 30. And Nadia goes out. She gets an average. She samples a bunch of people, not the whole population, but a sample, and she gets an average of 30. Now, let's say this is done an infinite number of times. Not really an infinite. I mean, it would be great if we could, but since it's a finite population, we would do this basically a lot of times. All right. And everyone came back. Maybe everyone sampled 10 people and they came back. And Nadia said, oh, my average was here. And Che said, oh, my average was also here. And Nate said, oh, well, my average was actually a little bit higher. And another person came back and said, my average was actually 40. Oh, one person came back and said, oh, I got a high average of 45. One person said, I got a 20. A bunch of people keep reporting this as the average. So people are returning back, and then they're graphing their averages from their samples. And that creates a sample distribution. Here's a quick picture. I'm not sure it's going to help. If it does, great. If it doesn't, no big deal. But let's consider this red curve, the population. Okay, now the population average, which we've discussed previously, is called mu. Now, these are people who are going out and doing samples. And they're not sampling the entire population. They're sampling maybe n people. In our first example, I said 2 people. Right? In this example, 10 people. But you go out and let's say that Nadia comes back, and this is her sample distribution here, and she gets an average of x bar sub a. She gets this average right here. Okay? Then Evelyn comes back, and she says, oh, well, I didn't quite get that. I got this from my sample, and this is my average right here. And then we have Cody goes out and he samples a bunch of people, and he comes back and he says my average was actually this, the green X bar. And that's done in theory, not in practice, but in theory an infinite number of times. And everyone comes back and they graph and they tell people, here, this is what I got for my average. So, you know, Nadia's X bar is here. Someone else might have come back with that same exact one. Cody graphs his here. Okay, and again, someone else could have come back with Cody's average as well. And then we've got Evelyn coming back with maybe a slightly bigger one than Cody. And another person comes in and says, hey, I got the same thing as Evelyn, or hey, I got the same thing as Cody. And you do this an infinite number of times, and it creates a curve, and this curve is the sample distribution. Now, something extremely powerful happens here. Listen very carefully. When we graph the frequencies that people are getting with their personal averages from their samples, when you are to graph that as a frequency chart there, and you are to draw your curve, the average of your sample distribution ends up being the average of your population. Always. I'll see if I can explain that a little bit better. Here we go. A sampling distribution is a probability distribution of a statistic obtained through a large number of samples drawn from a specific population. So here's the actual population. You know, obviously it's not a normal population. It's not a beautiful bell curve, but you know, let's say this is a number of basketball shots you made out of 50, right? A bunch of people made 7, a bunch of people made 6. Looks like this person made, I don't know, 13 or 14, and there were a bunch of people who made 13 or 14. Looks like only one person made 24 shots. So this is the population, and the average is 16. So we'd call this mu. Now, what's the sample distribution look like? Well, n equals 5, meaning 1,000,000 people, 1,000 people, tons of people go out and they do a sample of 5 people. And they all report back with their averages from those 5 people, and they graph them here with the frequency chart. Now, interestingly enough, this sample distribution is normal. Really interesting, given the fact that our population frequency chart here isn't even normal. Very interesting. And also notice that the average of our sample distribution is the same thing as our population mean. Very interesting. Now, How about a sample distribution where people go out and they survey 25 people? Well, when those people come back, I'm talking about thousands of people, millions of people interviewing 25 people. When they come back and they graph their averages, notice how the variance or the standard deviation is a lot smaller here, which makes sense because we're doing a bigger sample size. We're probably getting closer and more accurate to the actual average. But still, isn't this interesting that this is a normal distribution curve and our average of our sample distribution is the average of the population? That's incredible. Now, let's do some definitions here. The mean of the sample distribution is called the expected value or the expected sample mean. It is always equal to the population mean, right? If we go back to this picture, this is what we're talking about right here. That is the expected value or the expected sample mean right there. Okay, this is my sample distribution right here. So this is my value that I'm talking about. What do we call that again? The expected sample mean, expected value. And like I said, that is always equal to the population mean. Crazy. Wow. And I mentioned this before, but I think it's really interesting to mention again that even if the population is not normal, the sampling distribution is. When everyone comes back and reports their means from their sample distribution, from their sampling, the results are normal, right? Crazy. This is a normal distribution right here. I'm not saying, this is important, I am not saying that you should expect to get the population mean from any sample. I'm definitely not saying that. However, I am saying that if you performed all samples possible, given your sample size, the mean of all those sample means would yield the population mean. Let's read that again. I'm not saying that when you go out and you sample a group of people that you'll get the population mean. What I am saying is that if you performed 1,000, 1,000,000, 1,000,000,000 samples, and then you graphed your averages from those samples, then looking at that graph, the mean of those results from your sample means would yield the population mean. Okay, here's our first question. Consider a population of 1,000 people with a mean of 15 pairs of shoes. For a sample size of 100 out of this population, what is the expected sample mean? This question looks hard, but it tells you that the population has a mean of 15. Okay, what is the expected sample mean? Well, let's go back for a second. Remember, our expected sample mean is going to be the same thing as the population mean. So that expected sample mean is the same. So the expected sample mean is the same as the population mean. The answer is 15. There's no math involved. How about this one? Consider a population with a mean of 1.2 siblings. For a sample size of 80 out of this population, what's the expected sample mean? Come on, don't get tricked now. The answer is 1.2. That's the population mean, so that's the expected sample mean. What am I trying to say? Oh my God, the expected sample mean is the same as the population mean. Remember that. These problems are easy. You just have to recognize them. All right, now that I'm calmed down, we're just going to do one quick review slide before we move on. All right, if the distribution of data is normal, this is a throwback, what % of the data is what from the what? Well, we know that if it's 95% of the data is going to be 2 standard deviations away from the mean. That would have been an acceptable answer. What about another one? What if we said 68% roughly is going to be within 1 standard deviation of the mean? And then what's the last one? Do you remember? 99.7% are going to be within 3 standard deviations from the mean. All right, a person who is above average has a z-score that is greater than 0. Remember, if you are 0 for a z-score, that's average. If you are less than 0, you are below average. And sometimes that's good, sometimes that's bad. All right. A person who scores in the 80th percentile scored better than what percent of the population? That would be 80%, right? All right, that's a good review. Come back next time. I know this was a tough video. I hope you did well on it. Send me any questions. Remember, enjoy your life as much as possible. Pet your cats, pet your dogs, pet your arms if you want to, and enjoy your life. Okay, bye-bye now.